modes. And in that mode, we have shown that if I have to add a new mode or new transition or new behavior in our existing design, then considering that new effect from every state may make my design clumsy, and in that way it may happen that if I introduce hierarchy, that may make my design clear, more easy to understand, and that affects that improves my model in terms of my model. So next we will come to hierarchy part. If you remember, actually I have again taken this example as far as in our yesterday's discussion. If you remember, that there was some ambiguity, and maybe there is in the pending part we have some doubts, and I could not explain that better because I was not having that specification and the modeling side by side. Maybe I was talking about some other specification, but that was not matching with this design. Now let's just go through it once again, and from here we will get the notion that why concurrency is also important in our design. So let's start with this modeling. So what are my specifications? It starts in the wait state and counts 60 seconds with the help of the variable count. So just check the rate state, and from there this rate to green, to make this transition, you can see that I am checking my GERD or my transition condition, that is whether count is greater than or equal to 60. If so, I'm setting my signal G high and making the transition to green. And with that, what is my other action? Not only I'm going to the state green, I'm also setting my count value 0. So that in the next state, when I will be starting with this green part, green state, there I will start from count 0 and 1, 2, and so on up to 60. That way. The next statement in my specification is, it then transitions to green, where it will remain until the pure input pedestrian is present. That means you can see we have this input pedestrian that is deciding my next transition. Now there may be two possibilities. In the green state, that maybe the green state has been there at least 60 seconds or 60 counts in this, according to this model. If it has already covered 60, it is already completed its 60 counts, then if this pedestrian is coming, then the green state will move to yellow state. If not, the green will move to this pending state, where it will complete its count up to 60. You can see here from green to pending, the transition condition is pedestrian, and if pedestrian is high and if count less than 0, then in the pending state, it will go count to count plus 1 and so on. And when it is coming out from the pending state, you can see here count greater than equal to 60. That part is checked, and then the controller is making a transition from pending to yellow. See, for all other states, from when we are moving red to green or green to yellow, we are setting, in my action part, we are setting this count is equal to 0. But when we are going to this green to pending part, there see, we have just set count is equal to count 1. And we have not set this count is equal to 0 part, because in the pending state, wherever my count value was in the green state, from there I'm starting my next level of count. So this was the part of the traffic light controller we have discussed, and from the yellow, then again it is followed by my next specification. When pedestrian is present, the machine transitions to yellow. If it has been in state green for at least 60 seconds. Otherwise, it transitions to pending, where it stays for the remainder of the 60-second interval. So that was given according to my specification. Maybe other controllers, they work in some other way, following some other specifications.
Ma'am,
Pardon?
ma'am,
Yeah. Then,
yes, ma'am. Like in this, from green state, when we are sending the like transition, when we are transitioning to pending or yellow,
yes.
the condition is this one is intersection, right? Pedestrian intersection. Sorry, like both conditions should be satisfied. Pedestrian
And ending,
plus
exactly. Ending.
yes, no, and condition is there.
Hmm.
But we have not given the specification regarding when there is no pedestrian and the count reaches 60. Then what will happen at that time?
Exactly. That is the thing. That's what I want to mention. That at that in those cases, it may happen that if there is no pedestrian, that's why I was telling that there is some problem with this model. If there is no pedestrian, it may happen. According to that there will be no state change. Like if the state this model is in state green. Now see, if pedestrian is I mean not absent, maybe this input is absent. That means this condition is not getting satisfied, or maybe the next green to yellow transition. Both the transitions are not getting satisfied. That means ideally, according to this, it should retain its state green. But that also not actually specified properly. So that's why those are the limitations, fuzzy parts. So that's why we go step by step in the modeling in each and every state, and we have to check whether we have specified all these transition conditions properly or not. Otherwise it may lead to some amount of non-determinism. That we will see another type of non-determinism also in this connected to that. Just let me finish that. You're correct, that is not mentioned specifically that pedestrian, if not there, that input is absent, what will happen to this state machine? Where will it continue in that state green? Ideally, if nothing is given, it should continue in that state green because there is no transition specified. So there is a possibility that at that part there may happen that this FSM is getting stuck at that state. So those are the particular points, particular limitations we have to take care of when we are designing our own FSM. Okay, so that then the final. Okay, that was for your question, right?
Yes, ma'am. Yes, ma'am.
Okay, yeah. So
Ma'am,
this,
actually, one more question. Like
yeah,
in this from green to pending transition, you
yes,
said that we have put the count is equals to count plus one, so
yeah.
that the count keep on increasing until it reaches 60.
Hmm.
But ma'am, is it actually required? Because as soon as we reach pending, then also we are giving count is equals to count plus one.
You are
Like
telling, yeah,
yes, ma'am.
you're telling that if I am, let's say, at the green, my count is let's say 15, right?
Yes, ma'am.
15, and when I'm making a transition to pending, of course that is also possible that you can do the 15 to 16, I mean increase of that count value in that pending state, or here it is given that it is doing in the action part exactly at the transition. But when the
But
transition condition is satisfied, that is I mean increasing one count value. Yes.
ma'am,
Yeah.
but we are like mentioning it like is it like it is required that we have to mention it in the guard part also, like before
No,
the like
it is not required. See, these pendings, it is not always required. But what you have to ensure that when green is making a transition, see, pending state, you can think about some associated state with just the green state, right? Because you can handle the count value in any way. That doesn't matter whether this count plus one is taking place inside that pending state, or it is making a increase just after the transition before going to the pending state. Exactly
okay,
at the I mean when it is entering the pending state, because it is your main specification is that what you have to satisfy, that you have to be at least for 60 seconds in the green state. Maybe that is within the exactly green state or total green plus pending state. But what you have to ensure, when you are coming out from this pending, wherever you have increased that maybe that count value, but finally that count value is greater than, that is greater than equal to 60. That condition should be satisfied.
Okay.
See, wherever you increase the final check, that will make the transition from pending to yellow or green to yellow, right? That is fine,
Yes,
right?
ma'am. Yes, ma'am. Yes, ma'am.
So that is the important part. That is pending state. Here you have to thought of, setting is as a separate set. But you may improve this FSM and you may think that these conditions, these checking, you can put as a logic inside the green state also. That is also possible.
Yes, ma'am.
That is a, so that separate thing, that it is just they have followed the specification and shown that if I go by line with my specification, what will happen? And they have considered one extra state, that is pending.
Yes, ma'am. Whenever we are giving the guard statement, like
Yes.
this, should we always mention that the output, like after slash is what we give as an output, right? Like what will happen next. So should we always mention it, or like we can even write this pedestrian and count is less than 60? Like if we write that much, like will it be wrong, or like will it suffice?
Region, pedestrian and count less than 60. Yes, of course, that you can actually give inside the green state also.
No,
But
like I was just asking, like whenever we are mentioning any guard, not this particular guard, like
yes,
we are always giving the slash, like sig y, sig r after
any
that.
guard, for any guard and for any action, for I'm first coming to the guard, for any guard, you can actually concatenate multiple conditions in this and or logic. Okay, these are basically this is for and symbol. You may have some other or requirements to satisfy your full transition condition, right? So in any case, you can actually concatenate those conditions with this some and or logics, and then you can form your full guard. That is your transition condition. And after this slash, that is your action part. In that action part, it is not necessary that you will just you can set one single variable. If you have multiple variables, those are all your actions that you are considering based on these guard or based on this transition. So all these values you can actually set. Okay.
Okay.
So this is the this is, so now I think it is clear. Last it was not so clear, so now I think it is clear how it is following the specification. So the last line says that these ensures that once a light grows green, it stays green for at least 60 seconds. At the end of 60 seconds, it will transition to yellow, where it will remain for 5 seconds. See, check the state yellow. From there, when we are coming out, so it is again count is equal to count plus 1, and if it is less than 5, it remains in the yellow state, and from yellow to red transition, it is checking whether count greater than equal to 5. If that condition is getting satisfied, you are setting this signal R high, and you are in the signal R state. State R. You are in the red state. Okay.
Ma'am, I have a query.
Yeah.
Yeah, ma'am, if the pedestrian stop before in mainly the crossing side, so what happened?
Mainly the crossing side. When it is he is doing a crossing. He is in the crossing.
Yes, ma'am. Yes.
Right? Yeah.
Yes, ma'am.
That is, I'm coming to that. I'm coming to this pedestrians part. Okay. In the next slide, that is we will deal with. So this slide, it is purely from the traffic light point of view. Okay. Now here we are just considering that pedestrian as a control input, either absent or present, absolute pure signal, right? But we have to consider that pedestrian's point of view also. What may happen in that pedestrian part. Now, for that pedestrian part, you see, we just cannot consider that as a single input when the button is placed. As you mentioned, that there may be different states of pedestrians also. First state is that waiting. Waiting means when the pedestrian just came and then pushed the button. So that is entering in the state waiting. Now pedestrian is waiting for and checking for the whatever signals the traffic light controller is showing. And when it is red is high, that is your transition condition. What is the action? Waiting state is going to crossing, right? So it can continue. I mean, a pedestrian, he or she or they, whatever it may be, so they can continue in that crossing state till that signal green is high. Okay, so that is the signal green is the transition condition that denotes that now the crossing states of the pedestrian should go from some crossing state to some maybe idle state. Now here is a problem that we were discussing yesterday, that how this we talked about, remember, environmental modeling, right? And where we talked about that non-determinism may be an issue. So this is one example of that. See, when it is quite defined that someone is interested to cross and he is pressing that button. That means when he presses that waiting to crossing state, and then he or she will get that signal R, then signal G. So all these parts are very defined. So when you are moving, making a transition from waiting to crossing, that part is very defined. But when you are crossing, you are in the middle and crossing to going to none state. None means here we are considering both the cases inside none. One case is when someone has completed the crossing part. So signal G on, now someone will understand, okay, now wherever I am, I have to stay there, or if I am in the midway, I have to rush to the next part. So whenever, whatever may be the case, maybe I have just completed my crossing, or I am a pedestrian who is thinking whether I will cross or not. Okay. So this part from crossing to idle, this non-state means both. But here is ambiguity. It may happen, you will never know what will be the condition. I mean, I should not say you will never know. The proper thing is to tell that it is not properly defined. You cannot easily define your environment to check or to get the idea when any pedestrian will come and push that request that will say that pedestrian request high. So that's why I see this rate part when none to none transition. That means someone is idle or your environment is idle, and from there it is continuing to be idle. That part, that may be in some scenario when you are actually predicting what could be your possibility, that may be true. Again, from none to someone is coming and pushing the button and making this action, based on what your pedestrian is becoming high. Pedestrian control input is becoming high. That is also possible. So this part is, and you are modeling basically not exactly the controller, but your environment. But this part is not very deterministic, right? Because this part you are not very, it is not easy to model that at what interval or which transition condition you will give to make this transition from none to waiting. So this is something leads to very much non-determinism, and that maybe these parts should be taken care of, because of course this is in turn affecting our overall controller design, where pedestrian will come if that is very, that request is coming, in a too much frequency. If you are allowing that, that also will not good for your controller design. And there are many other issues. The thing is that these parts leads to these. That's why we were telling that this, in case of environmental modeling, that may lead to some non-determinism. Or in other words, we have to take care of different non-deterministic scenarios when we are thinking of our environment model. Okay. But whatever may be the case, okay, whatever may be the case, so far we have understood that at this point, we are not talking about a single FSM. We are talking about two dependent FSMs. One is that our traffic light controller and another is our pedestrian FSM. And those both are actually running concurrently and sending inputs to one to another. This pedestrian FSM, you can see, it is giving input to my traffic light controller, that is my pedestrian control input. On the other hand, my traffic light controller, that FSM is giving input this SIG, that is signal for green light, signal for R light. Those are also actually controlling the FSM transitions in this pedestrian FSM in the control. So basically, they are running in a concurrent manner, concurrent fashion, and they are communicating with each other, and their signals, their outputs are basically affecting with each other. That's why we are telling them communicating FSMs. And here concurrency comes into picture. Okay. Now think about this, not only this, this is just we are thinking about a single road crosswalk and single pedestrian. And single pedestrian may be pushed. But just think that if you are thinking about a 6-lane or a huge, communication, reach point, 6 point, where we are handling number of main roads, number of lanes and then by-lanes, and all those are controlled by these type of smart controllers. Then you have to not only, you should not think that I'm just controlling one single controller, traffic light controller. Basically, your single crosswalk controller is giving input to other mother controllers, to maybe other sublanes or other main roads. So this way, this is a huge problem of concurrency, or we need to handle concurrency when we are talking about FSM. So now formally we will go here. And you can see the concurrency extension allows us to use hierarchy to decompose a state into two concurrent states. See? Or conversely stated, to group two concurrent states into a new hierarchical state. Sorry. Here you see we have previously the same example. There we considered A1, A2, and they were making transition in that time. We have considered hierarchy inside them. Now come inside B. It may happen these B states you can actually compose to some substates. Those are C and P. That substates, C and D, you can again divide to some subsequent subsets. Those are C1, C2 within C and D1, D2 within D. That means you can go other way round. Initially, you can think that you have initial states from where you are defining the substates, and from there, those are your CD in this case. From there, you can go to define these substates we can tell D1, D2, D1, D2. And in your complex design, you have to ensure the fact that all this design, all these sub-FSMs should communicate in as per their requirement. Okay. So here you can see that C1, C2, those are just inside C, D1, D2, those just inside C. So this is initially from the top-down level approach. If you think that you have mother states, you are dividing them into substates. Or you can think about from the bottom-up approach also, where you have these C1, C2, then you can club them inside a single state C, and you have D1, D2, you can club them inside a single state C. Then you, as per requirement, you see, okay, these two states are communicating and they are running in a concurrent way. So we can think them as concurrent states. Okay. Now see. Now basically these are the two methods of using concurrency. One is or decomposition and another is and decomposition. So can you tell me what we mean by this or decomposition? Someone? Hello? Hello?
Yes, ma'am.
Yes,
So
ma'am.
it basically
Yeah.
basically decomposes by keeping only one state active at a time, like an OR gate. So if one state is active at a time, and if that state is decomposed into sequential state, then this would be OR decomposition.
Exactly. So here, if we think about this this diagram, these base state we are decomposing into C and D. Now inside C, if you see C and among C1 and C2, among them at at a time one state can be active. From C1 maybe C1 or C2. From D also either D1 or D2. One state at a time can be active. So this decomposition is of course odd decomposition. Okay. But if we consider D and its substates as C and D, in that case C and D both are running, both we are considering concurrent FSMs and they are under and decomposition. That means at a certain time they both are running and they both are active, right? So these are by names. You can directly understand. This is one is or decomposition and there is and decomposition. Now these are a few terms that I want to mention. But because before that, last year I also mentioned that these hierarchy and concurrency, these extensions was first mentioned in that state chart. And in that state chart, there are some other added constructs. When you will use that state chart software or when you will do your modeling, you may actually use them. Like one is that timeout. So the timeout is very similar to delay. Remember when we used here, we can go up here. When we have designed this, fire mode, there, according to our specification, that there will be some delay and after that the door will open. Then when we are actually modeling using these type of softwares, we are actually modeling this delay and those things. We can use this timeout or this type of construct. These are the few terms that will be used when we will actually use the software. Another important concept is history. History means, this is very specific to structure or direct hierarchy FSM. We will not see that in PSM, we will discuss later. History means when we have talked about hierarchy, remember we talked about that you are in state A maybe, and when this Z transition or Z guard, what I say, transition condition is getting satisfied, then you are coming out of A and you are making a transition to B, right? So when you are coming out from A to B, it is not known. It may be not known that whether you are coming out from A1 or whether you are coming out from A2. Okay. So that means for B, it is just you are coming out from A. But with this history added construct, what happens? The history is written that when with this gate transition condition getting satisfied, you are coming out from A, whether you are coming out from A1 or you are coming out from E. And according to that, it may happen when you are going back again. Maybe when W condition is getting satisfied, when you are going back again to state A, then you are actually going to the state A1 if that is stored in your history and you're not going to it. You're entering in the state A through state 1. So that is the advantage of history construct. So actually, to give an analogy to the in practical design, you can think this as an interrupt. Okay. When you interrupt, when there is an interrupt to your mother system, what happens? You have to store the details of your ongoing process, and then you can handle the interrupt, right? Your operating system actually stores the execution details of your ongoing process somewhere, and they shift to the interrupt. They shift to handling that interrupt, handle the processes related to interrupt, and when the operating system again resuming your halted operation, then it resumes from that state. So basically, it is maintaining the history of your interrupted state. So you can think similar concept. You can actually model similar concept with this history construct. You can think if your system is in state A and some interruption came that made the condition Z transition condition Z satisfied. Now your this GERD Z is satisfied due to that interrupt, and that's why you are moving to state B. So with this the help of this history construct, when the operations inside the state B is done and your system is again coming back from state B to state A, that means you have already handled the interrupt through the state B and you are coming back to your main system in state B. Then you can actually start from that state A1 you have maintained in your history, and you can continue your execution from there. So this construct is very similar analogy with our interrupt handling. Okay. So one is this timeout for timeout for our delay handling, and this history is related to our interrupt handling. Now there is now you know that what we mean by hierarchy and concurrency and how this extension in FSM helps us. Then we are mapping them with some sequential program model. And this merging generally technically termed as program state machine, PSM. Now, concept-wise, it is similar, nothing new. You can see here we have again taken this the example of our elevator, where we have considered two modes. Now my unit control, my initial mode was according to hierarchy. We have divided into two modes, normal mode and fire mode. And inside those modes, we are basically writing these sequential steps. Now, there is one thing. Sometimes the concept of PSM gives you the idea. Let's say you have a huge system. Okay, there you have to avoid ambiguity, to avoid non-determinism. You have considered all the different states and the detailed transition conditions. But when you are entering inside a state, maybe that is a small part, small module of your system, small state, and handling very limited operation. At that part, there is no reason, there is no requirement that you again identify all the states and the transition conditions. Maybe that is very small and that will be easy to handle with your sequential design. So at that point, what you can do, you can divide your huge system, huge requirement in different states and transition conditions. And inside your smaller states, or I can say smaller substates, you can directly go follow this sequential program model, because directly that sequential program model you can map to your existing tools. Okay, so that is the idea your PSM gives to you. And one important support related to your concept of transitions. Maybe this part I have already mentioned in the last us that there are two types of transitions this PSM supports. One is transition immediately, that we have taken the example of fire input is high. That time, whenever you are in your normal mode, whatever state it may be, idle, going down, going up, whatever it may be, you have to come out from that state and you have to move to fire mode. But when that is transition immediately. Based on that type of input, you have to make the transition immediately. But when you are inside this fire mode, that time it is different. Whatever may happen, you have to complete whatever the sequential steps you have inside this fire mode, and then only you can go back to your normal mode. Okay, so this is in fire mode, we are actually following the transition that is typically transition on completion. But in normal mode, we have to consider the transition immediate transition. So these are the two concepts of transitions we have to consider. I mean, when we are actually designing different types of modes, and importantly, if my software is not supporting these, I mean, what to say, this constraint we have to add to our design. So here, the PSM state machine, it is a different representation where you can see that there is a black box inside fire mode. In the left, there is a black box before an arrow. So when this black box is associated with an arrow, that shows that this is one transition on completion type of transition. So this is just the concepts. Maybe we'll not get this support, this type of different transition support in our state chart. But when we have to design, we have to keep in mind these parts, that which transition I should make immediately and which transition on completion. And then, of course, this is another example of request resolver and unit control. Those are going concurrently. Now we know that we need in different cases, in each of our, mostly in each of our examples, whatever we have taken, we understand this concurrency we need to handle in smart way. This is another example you can take where we are considering two concurrent processes. We are taking two inputs with X and with Y, and we are passing that to our print hello world statement. This is very simple concurrent program example. And when we have considered X as my input to my print hello world, we will be displaying this hello world with a delay X and some other printing other message in my print how are you. There I am printing how are you with some delay. Now these type of concurrent processes, this is very simple example compared to what we have discussed previously. But one important thing is to note that this is very simple. Why? When you have started this concurrent process C, you have only read X and read Y. And you have passed this to your print hello world X and print hello world how are you Y. You have passed these values to these two programs. That's all, subprograms. That's all. It is not that these print hello world or print how are you, the two programs, two processes, those are running concurrently. They are not exchanging anything in the runtime. That means it is not that they are not sharing anything. But if you think about your traffic light controller program, at that time, what happens? You think that requirement is something different. Their pedestrian, they have their own FSM and they are generating concurrently, they are generating that pedestrian control output. And your traffic light controller, they are updating and FSM is running, and that is concurrently generating that SIG-R, SIG-G, these control outputs. That in turn will work as an input to the pedestrian. So that means the requirement is that is not this type of simple concurrent process. That kind of requirement is these two processes should communicate. Okay. Is there any question? First, we should solve it and then we will go to the next part. Hello? Hello?
Yes, ma'am. No question.
Are you there?
Yes, ma'am.
Okay. Sleeping? If not, then I will go to the next part. Okay. So next, so what we have to do, remember, we have to design communicating FSMs. Now, how can you write that? When you know that you have your specification, now you have, I think by now you know how to write them in dividing them in states. I know, I think that now you can identify what will be my state transition conditions. Based on that, you have designed your FSM. Next, you know how to write that in terms of some sequential logic. Remember, we have discussed that in our previous class, where we have taken one example of this FSM finite state machine, and we have written those. Translated that to sequential program by mentioning the states as switches. We have taken that key switch, and inside that every switch value, we have written what will be my transition conditions in the if construct, and with that if construct, if that is getting satisfied or not, what will be my next level transition. So that is the step till now we know. But now after this, when we want to design these type of concurrent process models or processes, my added thing is that I'm writing one process while I'm translating multiple FSMs in that way, and now I have to share some variables, or I have to think of some means by which these two FSMs written in sequential code, they can communicate. Okay, that is my problem. So now writing concurrent models, what are the steps? Of course, either you can write them as a regular process, or a lightweight technique is you can take help of threads. Thread means what? You can think about them as lightweight processes. Lightweight process means what? That if you create multiple threads from one process, then these threads actually they share many things. They share the address space, they share system resources, and creating and storing these threads is not as costly. Costly means what? When we create process, we have to keep track of different things. Process ID, process state, and there are different parameters. We have to keep track of them. But when we create thread, those are not so complex. Those are with limited parameters. That's why when we are creating them, we are considering them as lightweight processes. So of course, if you have now think about your elevator control model. What you can do, if you have divided your FSM in sub-FSMs, sub-states, then you can assign thread one threads for one states, and you can take the help of this lightweight processes that will execute your states faster. Okay. So why we generally use thread? That is lightweight and that will be faster. The idea is you have one mother process, you are dividing them. You can divide them in multiple processes, or you can divide them into lightweight threads or sub-processes. Okay, in whatever way it may be, you have divided them. Now the question is, now how these two concurrent processes communicate? My pedestrian FSM will generate that pedestrian action. That is one some value, where I will write that value so that my traffic light controller FSM will also take that value and they will use that. So for that, there are two ways. One is that is called message passing. Okay. So message passing is like data transfer, information transfer. So your process A is sending some message to process B. Now you can see right this in the right side where there is something called message queue. Can you see that? In this diagram, there is something called message queue. So ideally, when we write something, writing this process, who is going to maintain that? My operating system. Operating system maintains one message queue because there are huge number of processes are going on running, and they can try to communicate with some other process. So in that case, process A may create a process. It may look like this. See this, send and some values and some parameters associated as well. And it can be received to this process B. Process A will add that message to this message queue. You can see it is inside the OS, and operating system is controlling that message queue, and that message queue will hold that message and the ID to that destination process. Based on ID, the message will be delivered to process B or process B to A and so on. That is one technique, how this sequential processes communicate. Basically, when you are writing your FSM in terms of two sequential different processes, then they can communicate by these two ways. You can see in this message queue, there are different messages M0 to MN, and they will be delivered to their destination processes according to the given process ID. Otherwise, the other way is you can actually communicate through this shared memory. Okay, that means you have one shared location. Maybe if I take my traffic light controller example, your traffic light FSM and your pedestrian FSM both are writing, because since they are just communicating based on few values, this pedestrian value, SIG, SIGI, these controller inputs, they will write in a shared memory location from where both the FSMs actually can read those values. So these are the main two ways: message passing or shared memory concept. Based on these two ways, your two communicating FSMs will share their values. Okay. So that way, when we are actually designing this complex, communicating FSMs or my whole embedded system based design, where we have to handle numbers of such communicating FSMs, there are two ways. How where I will offload this, working process, this handling of messages or this handling of shared data. One way is you can trust whatever platform you are choosing, that platform is associated with some hardware. Hardware means your ALU logic, your control unit, your your memory part. So that part, and on top of that, when you are writing processes, they are getting communicated with the hardware with intermediate layer, that is your operating system. Operating system is nothing but a program, some set of sequential instructions, not sequential instructions, set of instructions. These instructions actually control this message passing, sharing of defining the protocols, sharing of data, everything. So this operating system is helping you in your multi-task. But when we, of course, we can choose one platform, we can trust in that operating system, we can write the sequential programs there, and we can define some shared variables, define some shared memory locations, and we can do the communication in that. That is possible. But since we are dealing with embedded system, we will see that things are not so straightforward. Always when you choose some platform, it may happen that will not supporting, I mean, that will not be enough to support your real-time constraints. I think by now you know what we mean by real-time. Real-time means you have some particular deadline to meet. So that's why for that real-time constraints or RTOS operating systems, sometimes we trust on some RTOS schedulers, or sometimes if our constraints are too specific and that cannot get supported by existing processors or existing platforms, then what we do, we design our own RTOS schedulers. So these schedulers actually help us to control how we will handle these multitasking scenario, how we'll handle these different communicating FSMs, and also we shall try to, match whatever our real-time constraints are. So this part, whenever the discussion will come in the, second part of this course, Professor Sharkar will take more, give you more insight about this RTOS operating system, its scheduling, and how this schedulers can be designed or can be modeled first. So this part will be taken in the next part of this course. Just as of now, we will concentrate on this hierarchy, concurrency, and in the next day. So as of this is, for today up to now. Next day, we will see some more detailed example of hierarchy and concurrency in our actual embedded system design. Now, where is the challenge here that we have not till now discussed? That is, our embedded systems are hybrid in nature. Hybrid means there, of course, you will deal with some FSM, but that FSM should support both continuous type of signals and also discrete. So first we have to model our FSM in such a way that is capable of handling these type of inputs, and then only we will discuss that how this hierarchy, concurrency, these extensions of FSM we can handle in our hybrid system. So that part of discussion we will take next day. Okay. Just one thing I forgot to mention, that when we think about not multiple processes but multi-threads, then there are some existing libraries. There are POSIX and all. There are different libraries in 32. So that can be merged with our sequential model design. That will give you the idea of multitasking, where to improve your multitasking design. Okay. So that's all for today. Maybe from next day we will discuss about hybrid system, and then we will come back and take some more examples of this hierarchy and concurrency. Okay.
Okay, ma'am. Thank you, ma'am.
So
Thank you.
welcome. So that's all for today. I have uploaded the slides. I hope you have seen.